Hello, this lecture is going to look at the line shape function. That is, for example, when we have absorption, we have seen that the absorption coefficient A of nu, which depends on the number density of atoms, the charge square, there is these factors which we have derived a few lectures back at the classical model, and times the line shape function, which what we had derived was a Lorentzian. So the property of a line shape is that when I integrate from 0 to infinity L of nu d nu, this is going to give me 1. It's a normalized line shape usually. Now Lorentzian is one such possibility, but as we will see, this is not the only possibility. There are different kinds of line shapes. So for example, we have seen two examples of physical processes that lead to Lorentzian line shape. So one was the spontaneous emission, right? And we call this process as natural broadening. And the second process was power broadening that we just saw in the last lecture. So there are processes, and both of these processes actually lead to the line shape being Lorentzian. So in general, one can write down the absorption coefficient A nu as the prefactor E square 4 epsilon naught mc times the line shape function, which in general could take a form not necessarily Lorentzian. For instance, we will look at a Doppler broadening, which results in a Gaussian line shape in contrast to the Lorentzian line shape that we have seen until now. Again, the property of a line shape needs to be uh, followed, which is that the area under the curve is normalized. That is, my S of nu d nu would be 1. Now, so this is the general setting, and different physical processes lead to different kinds of broadenings of the line shape. So what we are going to look at today is the collisional broadening. That is, I have a collection of atoms which are moving around, for example, atomic vapor or a gas, and these atoms they collide with each other. What the collision does is that these atoms are responding to an external electromagnetic field which is driving the atoms at its frequency omega, and the collisions basically interrupt this response, this driven oscillators. They are repeatedly interrupted, not necessarily in a periodic fashion, but at arbitrary random times. The dipole moment generated in these atoms is repeatedly interrupted by collisions. So what we are asking is, by accounting for such physical processes, what is the change in the line shape that occurs? So we are looking at collisional broadening, and now let us just make some assumptions. So the first assumption is that I'm looking at atoms as billiard balls kind of collision. What it means, the collisions are instantaneous. The collision time, the duration of collision is much smaller than the time between collisions, right? So the collisions almost can be considered as instantaneous, right? So collision time is much smaller than the time between collisions. The next assumption is that I have a oscillating field. I got a polarization of the oscillating field. So if my oscillating field polarization is epsilon, then the dipole moment which I generate, right, is along the same direction. That is, the dipole moment x cap is going to be such that my x cap is going to remain parallel to epsilon. The generated dipole moment is in the same direction as that of the electric field. So at collision, there is a reorientation of the axis of oscillation. right? It's randomly gets reoriented. The dipole moment oscillation within the atom is interrupted by the collision, and at collision, the axis of oscillation gets reoriented. Essentially, we are trying to capture the statistics of large number of collisions, and you're asking how we are going to deal with it mathematically and what is the consequence on the line shape. Now you would recall that we had actually looked at the following equation when we looked at the Lorentzian line shape and looked at the model, classical model of the dipole moment of an atom, which was our Lorentz model. So if you recall, my original equation was of this kind. I had d2x over dt square plus omega naught square x equal to epsilon times, which is the polarization of the incoming field, E by m, the electric field associated with the electromagnetic wave at the location of the nucleus. Right? So you recall this. Now, for the Lorentz model, what I had done was I had included in this equation a dissipation term, which depended on the factor beta, which was precisely what determined the width of a Lorentzian. Right? So now I want to arrive at this dissipative contribution precisely because of collisions. So to begin with, I am looking at an equation which does not have any dissipative contribution as such, right? So at the moment, I'm now going to include this dissipative contribution in my model, and I want to just construct the model for collision and see what happens. This is a mathematical trick. So I had x was my displacement, right? This was a real quantity as we began earlier. Now I'm going to consider S as a complex displacement. So let us see how we deal with that. The way I'm defining S as x, the original displacement, plus I times P, which is the corresponding momenta associated with that displacement, divided by m omega naught. This is my definition. By the way, this is just a mathematical trick, but it gives us a very nice and interesting insight into the line shape function, right? So this is my new displacement that I need to worry about. And I know the following. There is a relationship between x and p, which is that my displacement dx over dt, right, which would be same as velocity, is simply my momentum divided by the mass, right? So in this case, which is the reduced mass associated with the uh, electron nucleus system. So consider the following equation. This equation is important, and once you get the hang of it, you will see that it kind of captures my earlier equations pretty well. So let me call this as equation number one, right? My original equation that deals with the dipole moment associated with a classical atom, which is a driven system. It has got its own natural frequency associated with the spring constant and so on. And this is my equation number two, which relates now these two quantities, which is the displacement and the corresponding momentum. So I can write down the following, that is d by dt of this complex displacement now, p by m omega naught, plus I omega naught complex displacement is equal to, on the right hand side I have of course I times epsilon. Epsilon continues to be the polarization associated with my real driven system, and it is E by m omega naught now, capital E R T, which are precisely the external drive. Let me call this equation number three. So if you look at the real part of the equation number three, right, you see that right hand side there is the real part of the equation is 0 because my external field was real, and on my left hand side there are only two terms that contribute to the real part, and you see that you can check it for yourself. The real part of equation 3 actually implies the equation 2. Absolutely similarly, if you look at the imaginary part of equation 3, actually this would imply the equation number 1. So you can check it for yourself and convince yourself that this is indeed true. So what we have done is we have simply generalized the displacement to a complex kind of a displacement. And there is nothing new that we have written in this equality or this equation. All that it simply states is states two important facts, which is that my original system, which has got no dissipation, it is got to do with the real displacement driven by a real external field. Everything is real in equation number 1. Similarly, equation number 2, everything is real, but one can write both of these together in this complex form, and let's see how one goes about dealing with this. In a sense, what I have done is to write the following equation, which is d by dt of s, which is my complex displacement, is simply I omega naught of s equals I epsilon by m omega naught e times E, which is a electric field associated with the electromagnetic wave at the location of the atom. So now if you invoke all these assumptions that I have made, which is that the billiard ball kind of collision times are much smaller in comparison to time between collisions, polarization gets interrupted periodically because of collisions, and it's in the same direction as epsilon. Pictorially, let me look at it this way. Uh, Imagine that my atom is evolving under the external electromagnetic field. This has got the same frequency as that one, and it gets interrupted at different times and then starts evolving again, right? Uh, and so on and so forth. So you see that there are multiple instances at this instant, at this instant, at this instant. There are multiple instances at which collision kind of interrupts this uh, the evolution of the atom. These these instances are roughly on an average, they happen at the rate of gamma c, right, which is the rate of collision. Average time between collisions is 1 over gamma c. Now let us look at this problem in a statistical manner. So imagine that F is a fraction of atoms which have not suffered collisions at the time t since another time t1. So let me state it carefully. So I'm introducing F to be a fraction of atoms which have not suffered a collision since t1. So this is my evolution of the time, right? So T1 was the last time instant where atoms suffered a collision, certainly. And I'm looking at another time t, and I'm asking at this time t, what is the fraction of atoms which have not suffered a collision between this time t1 to t? This fraction is what I want to obtain. So my f at a time t plus delta t. So I'm looking at this following quantity. I'm looking at now the fraction of atoms that have not suffered a collision in at the time t plus delta t, right? Of course, they had suffered the collision at t1. So what are the fractions that have survived the collision at this time? Is I'm looking at now in my timeline, I am saying, exaggerating, This time is my t plus delta t. So clearly delta t is this time interval, right? So I am asking what are the atoms that have survived until t plus delta t? This is my left hand side. And you see that the atoms which are remaining are the ones who survived until the time t, and you subtract the ones which suffered the collision in the time delta t. So this is a fraction of atoms who suffered the collision within the time interval t to t plus delta t, right? These are the ones who suffered and hence are to be removed from this counting of the ones which have not suffered a collision, right? So you can see that I can quickly rearrange this. I can write this as f of t plus delta t. All of them have suffered the collision at time t1, and I will take my delta t at the bottom. Again, so this is precisely, what is the nature of this billiard ball-like collision. What one is basically emphasizing is that there is no, this is a memoryless process in the sense that it doesn't really worry about the time t itself. What matters is the interval delta t, whether it is beginning at a time t1, t2, t3, t4, that really doesn't matter. The collision simply depends on the time interval delta t. So hence this is what is known as a Markovian process, which is does not have memory. Uh, it it is not as though if the first collision happened, the second has to happen, and so on and so forth. There is no memory of the previous collision. Each of them are random independent processes. So this top equation, as I said, can be rewritten in this following form, which is minus gamma c times f t t1. To this equation, if I add the following, that is, if I take the limit of delta t tending to 0, I will clearly get the following equation of motion for the fraction of atoms which have not suffered collision, that is df over dt is simply minus gamma c times f, right? And from this I can quickly get my solution, that my f at t with those who have suffered at t1 is simply given as, right, exponential minus. I can rearrange uh, my equation, and what I would get is exponential minus gamma c, and this is t minus t1, right? So indeed, at time t equal to t1, atoms suffered a collision at t1, and as I go further away in time, the fraction that remains is exponentially smaller, right? That is what this is clearly telling us. So what I'm going to do is the following. Clearly, there is nothing special about the time instant t1. I'm going to integrate now all possible values of t1 from minus infinity till the time of observation, and see, by integrating this, I would have accounted for all possible atoms and all possible collisions within this statistical mixture of atoms, right? So what I mean is that if I'm looking at the use this top equation, equation number 4, let us say, and use 4 to get this. So I can write this down as simply exponential minus gamma c itself, and this is gamma c times dt1. My claim is the following, that if I integrate from minus infinity till the time t, right, of d of f, you see that this quantity will give me 1, right? Clearly, this gives you some sort of a probability density or probability distribution associated with this with these collisions. So that is my probability distribution which I have to worry about. So let us come back to my complex displacement S. Uh, and what I'm going to do is I'm going to look at the complex displacement which is, sort of averaged complex displacement. That is, I'm going to define this as the average from minus infinity to t S of t gamma c, which is my df, f of t comma t1. What I have done here is basically I'm calling it now the collision averaged displacement. So this quantity basically gives me a s of t. Is that okay? I've integrated over dt1, which is the occurrence, definite occurrence of the collision, and we have basically integrated respect to this distribution function, which is same as this distribution function. Important point to recall that my complex displacement S T1 T1, right? This is my initial instant where the collision happened. This is equal to 0, right? So essentially what I'm saying is that my S of t at time t equal to 0 in equation 3 was basically 0. You know, why? Because you see that this is where the physical input comes in. Remember that my x and p at collision are random. And remember that these are vectors. So if I'm looking at all random orientations of these vectors, statistically averaged atom, and for that, the average is going to be 0. So this I'm calling as equation number 5. So if I'm looking at the time derivative of equation number 5, that is I'm looking at d by dt of, I will just write down as S average, right? Then you see that because d by dt has nothing to do with the variable of integration itself, which is t1, I can take it within the, so I can call this as ds by dt gamma c f t t1 dt1 plus s times, which is tt1. So again, this equation can be expanded, and we know that from equation number 3, right, I can get the form for ds over dt. So this will give me essentially minus infinity to t. ds over dt will give me minus I omega naught s, right? I should be careful with my vector signs. I epsilon e by m omega naught, the electric field r comma t, which by the way is completely unaffected by collision, this multiplied by gamma c f t t1 dt1 plus the second term, which I will write it separately as minus infinity to t s of t t1. And you see that df over dt will give me a minus gamma c outside. So let me call this as minus gamma c square f t t1 dt1, right? So this equation I can quickly rewrite. So you see that the first term, so look at the first term, I'm simply averaging over that. So this simply comes out to be, uh, if I perform the integral, the first term is going to be omega naught S average, correct? The second term is going to be plus I epsilon E m omega naught. There is the integration will give me just 1, right? So this is simply remains as E R T. Then the third term is simply going to give me minus gamma C times average S, and that's about it. So if I put all of this together, right, and remember that on my left hand side I had ds over dt for the average value of S. So finally, what I have is the following, that I have d by dt of S. Now I'm collecting and writing in the form that is quite equivalent to what I'd got earlier. So plus I omega naught, and I have got gamma C there. So I have pulled out I. So I can write this as omega naught minus I gamma C. Please check. So I times I will give me negative and a positive sign. That is correct. And this is multiplied with S. This equals I times epsilon E by m omega naught, the electric field associated with the electromagnetic wave. So this becomes my new operational equation, and you can clearly compare equation 6. I would urge you to compare equation 6 with equation 3, and you will see all that one has done is basically introduced this factor, right? We have introduced a complex frequency. So now if you compare these two equations 6 and 3, you will clearly see that there is this extra dissipative term, extra dissipative sort of term that you obtain, right? So let us see what we get. So what I do now is the following. I separate out the real and the imaginary parts of equation 6, right? This is precisely what I have to do. That's my next step. So if you do that, you will get the following. So the real part, clearly on the right hand side there is no real part, and again we have to make sure that we keep in mind the definitions of uh, S. My claim is that S by definition is X average plus I times P average by m omega naught. This is just the modification of the original definition that we had, and one is saying that this is how it is going to remain equivalent, right? So I use separate out real and imaginary parts, use this definition of now S, right? And see what we get. So you see that the real part of equation 6 gives me the following. So you can see that it's basically gives me the fact. So I have to plug in all the real and imaginary parts. I urge you to do the details. I'm simply writing down the result. So you see that the real part actually gives me the following. Now these are all average quantities. P by M is d by dt of x plus what you will see is gamma c x. This is what real part gives me, whereas my imaginary part of equation 6, so it will give me 1 by m omega naught dp by dt plus omega naught x average plus gamma c by m omega naught p average is equal to epsilon e. So these are the two equations that you get. Clearly between these two I can eliminate P, right? And basically eliminate P and retain only the x and its derivatives, right? So if I do this, you will see that I can come up with my final form of my equation, which is the following, which is d2x over dt square. All of these are, remember, statistically averaged, plus twice gamma c dx over dt plus omega naught square plus gamma c square x, which equals epsilon e by m. And I have the following. You know that the collisions do occur quite frequently in normal time scale, but you see that my omega naught much larger than gamma c square. So essentially I can neglect this term from here, right? So you'll see that now you can recognize that this equation is precisely the equation that we got earlier from the Lorentz model, where you see that 2 gamma c, the role of gamma c is played by essentially beta, right, in our earlier discussion. So uh, clearly you will see that this for example gives me the line shape which is Lorentzian. Okay, not just that, it is giving me a line shape wherein the width of the line shape is determined by the rate of collision, right? So if I'm looking at remember we had looked at the Lorentzian line shape L of nu uh, that we got, and we had delta nu naught as the line shape. Clearly delta nu naught here is gamma c by 2 pi, uh, right? Which is equivalent to saying that 1 over 2 pi times the no collision rate. So imagine that you had a atom which had spontaneous emission decay, and it was also having this collisional broadening mechanism, then you see that my delta nu naught will have multiple contributions. One of them is coming out of that A21 by 2, plus you would see that you have this gamma c by 2 pi would be this extra term because of the collisional broadening. You would see that my original Lorentzian line shape has now got broadened because of collisions, right? Um, so this factor could have been just, you know, A21 dependent, but now this factor has got two contributions, one coming from gamma c, plus you have the factors coming from A21. So you see, this is what is happening to the line shapes. As there are multiple other mechanisms, the overall line shape, overall interaction between the light and the atom actually decreases. And not just that, the line shape itself gets broadened. So collision leads to this extra, broadening of the Lorentzian line shape, and that is what is captured by this analysis. So let us now estimate how does one obtain this the numbers for the collision rate. These can always be obtained through experiments. However, let us just look at it whether we can get an order of magnitude estimate using what we already know. So for example, from kinetic theory of gases, we know that if there is an atom of mass m, right, um, then the average, the mean velocity of the atom, or the VRMS, is given by this formula, 8 kBt by pi times m square root, right? Here T is the temperature in Kelvin, right, in degree Kelvin, uh, and the gas is at equilibrium. Of course, what we are interested in obtaining is not really the average velocity, but what we want is an average relative velocity. So what our interest is to obtain relative velocity, because you see that collisions are going to depend on the relative velocity with which the atoms are coming towards each other, right? So it's the relative velocity that's going to play an important role. It's a V relative sort of average. And to get this number, what one does is simply replaces the mass in this above equation, the mass of the atom by something called the reduced mass of the two species which are colliding, right? So for example, if mx is the mass of one atom and my is the mass of the second atom, then you see that we will replace this m by the reduced mass of this system, so that what you get is basically the following. You will get 8 kBt, T is the temperature at which the gas is, pi, and now what I do is I write it down in terms of the reduced mass, which by the way is simply, let me first give you the definition of reduced mass. So mu xy is the reduced mass of the species. It is simply 1 by mx plus 1 by my and the inverse of it, right? In other words, it is simply mx my by mx plus my. So this would be the reduced mass of the system. So all that I do is, to get the V relative, I just write it down in this fashion, which is 1 by mx plus 1 by my. And you can clearly see that this is going to work out to the power of half. So this becomes my formula for the relative velocity in this system. And so now let us understand what does the collisional cross section depend on. right? So imagine I have an atom which is stationary, right? And then it is bombarded with atoms, which are coming at a certain rate towards it. So imagine that this is my target. The number of atoms per unit volume, right? Atoms, per unit volume is n, and you have sigma as the collisional cross section between the two species, right? And imagine that v relative is the relative velocity between the two. Then you can see that the number of collisions I can quickly estimate is essentially going to be the number density times sigma. That is going to give me essentially the flux uh, times v relative is going to, this is going to give me the flux of atoms. So look at this. This is 1 over n is 1 over length cube. Your sigma is length square, and uh, v relative is length over time. So essentially it gives me a rate, or 1 over time. For the v relative, I make a small change, which is I, rather than looking at the absolute mass of the atom, let us look at atomic masses or molecular masses. Then you see I can basically replace 8 kBt by pi times Avogadro number of in ideal gas situation, and where capital Mx and capital My are the associated molecular or atomic masses of these systems, power of half, right? And you see that this kBt times n, this product can always be replaced by the gas constant R, right? Universal gas constant, which is 8 RT by pi, where Mx and My are the molecular weights for the corresponding species of atoms which you are interested in, and this to the power of half. Right. So I will, let me write down now the formula for our collisional rate. So gamma c is going to be given as a sum over all the species that are colliding with my particular atom. Ny is the number density of the species of atoms y which are colliding with my atom, which is the stationary atom x, and it is colliding. So sigma xy is the collisional cross section between the atom at rest and the one which is coming in, and v relative, right, is the relative velocity between these two species. So you see that one can reasonably use such a formula and obtain some value for gamma c. And I would like to go a step further, and that is to basically estimate even what is the value of sigma, right? So sigma xy, as I told you, is a collisional cross section. Simplest model to arrive at the collision cross section is that of collision between hard spheres. Imagine dx is the uh, diameter of uh, the species x, and dy is the diameter of the species y. Then you see I can basically write down the collisional cross section as arising out of something like this, right? This is the hard sphere collisional cross section. This is an underestimate. Using having a model of an ideal gas, one can relate, for example, the number density to the pressure of the gas itself, right? And that helps us basically also relate the um, collisional cross sections with the pressure of the corresponding gas. One quick clarification here, y species one is talking about, one is also summing over x itself, right? For example, if I have a collection of gas which has, let's say, helium and nitrogen and carbon dioxide, for example, and I'm looking at carbon dioxide, looking at uh, the collisional cross section associated with the essentially carbon dioxide molecule whose line shape I'm interested in. So then when we look at the collision between carbon dioxide and nitrogen, and carbon dioxide and helium. So you see, these are the various species Y that you need to sum over to get the collisional cross section of the species X. So the summing includes the X species as well. I can write down another small formula. These are formulas that uh, uh, allow you to come up with numbers easily. For example, the number density of atoms can be written down in the following form for an ideal gas as some 9.65 into 10 to the power of 18. You provide the pressure in torr. For example, it's if it's a 1 atmosphere, then the pressure is 760 torr divided by the temperature at which the gas species is, right? This is a formula coming from the ideal gas model. So you see, one can arrive at number densities. Then V relative can also be appropriately obtained by looking at the molecular weights of the corresponding species. And one can obtain, for example, the uh, collision cross sections. So putting all these numbers together, one can actually estimate. And for example, the from such a estimate, uh, the gamma C. This is for a specific example of carbon dioxide molecule at 300 Kelvin, it at 1 atmosphere, right, which is 760 torr. Gamma C comes out to be 6.6 into 10 to the power of 9 second inverse. So you can clearly see that my uh, collisional broadened line width, right, is going to be gamma C by 2 pi, which is of the order of 10 to the power of 9 hertz. This is much smaller. So you see that whenever you look at gases, we still talk about, sharp spectral lines or absorption lines rather than absorption bands. It is simply because in comparison to the optical frequency, right, these are certainly very narrow. Um, so you're talking about 10 to the power 14 hertz with respect to a width of about only 10 to the power of 9 hertz, right? So this is the kind of numbers that one deals with when we are looking at gases. Uh, but then this discussion is important because it tells you that there are various mechanisms of line shape broadening, and we have just dealt with something called the collisional broadening mechanism, and um, this leads to essentially a line shape which is Lorentzian, and one gets an extra width to the Lorentzian line shape, which depends on the rate of collision that the specific atom or molecule faces within such a collection of gas. So the next topic that which I am going to deal with is basically another broadening mechanism, which is called Doppler broadening.